Hello, it's Duncan. In the last episode we looked at generating multi-word anagrams. That went well, but the resulting code was too slow when set to work on a long phrase. Like many of you, I suspect, I like a good optimization session, so this week we'll look at where that code is spending its time and see if we can get it running a bit faster. Since the last episode I've rationalized the tests a bit, so we're only now testing the anagrams for refactoring 2, and we've got this test here which is a slow one that we can enable with a system property. I've extracted the code for the anagrams out into its own file and put everything in an anagrams package. And I've added anagram speed test that measures the speed of anagrams for refactoring 2. And this uses some code that I pulled from the Gilded Rose project, which times 5 repetitions, discards the slowest and quickest, and then calculates the mean and standard deviation. So if we run this, you see it takes a little time and tells us that it calculated the anagrams for refactoring 2 in 1.485 seconds, plus or minus 45 milliseconds. This standard deviation is quite high. Normally if we run it, we get a better standard deviation. So our mission for today is to speed up the anagram generation, and we'll know that it's speeded up because of the speed tests, and we'll know we haven't broken it because of the approvals tests in anagrams. So if you remember, we're checking that these are all the anagrams of refactoring 2. So we're going to settle down into a nice little loop where we try to optimize something, run both the tests so we see whether it works, and we check that it runs quicker. And so this is our baseline, and it is 1437 plus or minus 29 milliseconds. Okay, the code we're optimizing is on the left here, anagrams. How do we know where this is spending its time? Well, we can find out by asking IntelliJ to run this with a profiler. So let's run just this. And this will run our code and periodically sample it to see what routine it's in. Okay, there we go, and now we can open the results. Now the default view is this thing called a flame graph. In here you can see the different functions and the functions they call and so on down here. And the width of this line tells you effectively how long it's spent in there. It's actually how many samples were taken, but as the samples are periodic, that corresponds to the amount of time spent. So you can see that we're in JUnit for a bit, and then we're in collections for each, and then another for each, lambda for each process. And down here you can see that we're seeing our recursive call. So it comes in process, and then process in process, and then process in process in process. On the left hand side we get to choose the threads, and this is all the threads merged, but in fact we're only really interested in main. Don't suppose that makes much of a difference, because we can focus on main, which is where our test is being run. Okay, so looking at the width of these, you can see this could be made from the letters in, appears here, and here, and here, and so on. So could be made from the letters in is the thing that's taking really most time that we've written. Let's have a look at that function. I don't know what I did there, but let's go and have a look at the function itself. And you can see here, for could be made from the letters in. We're spending most of our time in two mutable lists, so that's here. So we've got the letters and we're creating a mutable list out of them in order to remove letters from that list to find out what's left. It turns out what I did was zoom in, because you can see an echo left and right in here. So let's zoom back out again and we'll get back to the view we had. Okay, why is two mutable list expensive? Well, in fact, you can see here that two mutable list is itself composed of two collection on a char sequence. So let's ask what we could do instead. What we could do is just go and get the char array and then make a mutable list out of that. And now we can run our tests. And we see that actually made things a little bit worse. We had 1437 and we've now got 1469. So that wasn't all that successful. Now looking at this code through a performance lens, there are a couple of big problems. One is that we're going to have to box every character to put it into a list, box it to treat it as an object. And the other here is that every time we remove something from a mutable list, we have to shuffle everything up into its place. So remove from an array list involves copying a lot of data. Now these aren't necessarily big amounts of data, but we're going to have to do it every time we remove a character, every time we find one. So we could find a solution to both of those. And a solution to this is to start with just a character array. And we'll call this now remaining letters. And instead of removing the letter from it, we're going to mark it. So what we're going to do is we're going to say, let's find the index of the character. Now, if that's -1, then it's not there and we return false. So if index -1, return false. Otherwise, well, we can replace the character in the character array now with something else. So what we can say is remaining letters at that index, and I'm going to use a star. Now, if that character won't be available to find the next time, so it'll be the equivalent of removing it. Let's take that out. I'm going to run all of our tests so that we know that it works and we can see whether it's quicker. Well, that not only passes the test, but it's dramatically quicker. It was 1437 before and it's 932 now. But it's so much quicker it's suspicious, so I'm going to run it again just to check. But no, that actually is a speed up, which is brilliant. That one change makes things about 30% faster. Let's go back to the profiler and see what's taking the time now. Well, you can see now that it's minus letters in, and that's unsurprising because that is effectively the same algorithms we had before. There's another view we can use here, in fact, which is the method list. And this shows the total amount of time spent. It's got a lot of JUnit rubbish at the top. But down here we can see that minus letters in, that of the 505 samples, 333 are spent in minus letters in. Of those, only 9 is spent actually in the code, 270 are spent in this two-mutable list. So let's see if we can do the same job here. This is going to be remaining letters, and that's this to char array. Now we're going to do the same thing in here. But if we can't find the letter, we know we made an error in our previous could be made from the letters in. So we're going to take this into there. Once we've finished, though, we need to filter out all of these stars. So we take the remaining letters and filter it is not equal to the star. And that will give us a list that we need to convert to a char array. And then we can make a string out of that. Okay, let's run all of our tests and see how we're doing. Well, that gives the right results, and it gives them in 866 milliseconds. So we've knocked off another 70 or so. Actually, given the standard deviations, it's difficult to know for sure. And I'm getting quite high standard deviations at the moment, and I think that's probably because I'm recording the screen for this video. But I think we're going to assume that's quicker and press on. Okay, here we are in the method list, having run the profiler again. And you can see that now could be made from the letters in and minus letters in are both taking about 90 samples. If we start from could be made from the letters in, we can look at all the ways that it's called, merging the callees. You see this is spending 78% of its time in string for each. String to char array is taking a time, and length is taking its time. So this strings for each here is our loop here. It doesn't look as if we've got much we can take out of that. Going back to our method list, so we'll look at minus letters in and do the same thing. Here you can see that collections to char array is taking some time, and building our string is taking a bit of time, but on the whole, again, we're spending our time in this for each loop. If we're going to do something about converting to and from char arrays and strings, we're going to have to do something structural, and so I think it's probably a good place to check in. Also, before I do, because we've made everything a bit quicker, I've upped the repetition to 10 here so we get better resolution. And you see currently that says we're running around 760 milliseconds. So I'm going to commit this as use char arrays rather than list of char. Now we can avoid some of this conversion by noting that up here we're effectively feeding the output from minus letters in back into our could be made from the letters in. So that if we started with could be made from the letters in taking a char array itself, then we'd have to change this to size, but we wouldn't have to do that. so remaining letters would just be the letters. Let's see what that breaks. Well, our input then would have to be a char array. Well, that's not disastrous. We can change that here, and we can change it here. Now let's find the next compile problem, and that is input minus letters in. Our input is now char array, so we go down to here and say this wants to be char array, and again, now we don't have to get the letters out. One more break here is that remaining letters wants to be a char array and is now a string. But if we go back here, that's good for us because we were creating a string down here. So we can remove that and make this char array. So that compiles. Let's try running it. Okay, we have an issue in our test here. So let's just fix those with to char array. We change our internal interface effectively. That one as well, and run. Oh, no, that's not good. In fact, it's bad. How does that happen? Well, this happens a lot when we optimize code. What we're doing now is we're sharing these char arrays everywhere. We're sharing them, but we're mutating them because we are putting these stars in. So before we can change them, we have to copy them. That will obviously make things a little less efficient, but should get things running. That seemed to be a peculiarly slow run. Let's try again. So in fact, this change seems to have made everything slower. That surprises me, to be honest, but I'm going to git stash and try running again. And now we found that our baseline has gone up to 926, and I wrote down before was 766. So something weird is going on. And I think that weirdness is here. You may be able to hear the fans whirring on my machine. The problem, I think, is that laptop processors are thermally limited, and so macOS has slowed things down because it's having trouble cooling this machine. So I'm going to wait for everything to cool down. So another run with the strings on a cool processor gets us back down to 780 odd. Let's git stash pop and run again with our char arrays. Well, it does just seem that slower, which is a surprise to me, but there you go. If I run the fans at full speed, we do seem to be able to get this running a bit quicker, but on the whole, I don't think it's worth it. So I'm going to roll back those changes and just check our baseline speed again. So it looks to me like 10 repetitions has actually just made things worse because it's allowed the processor to get hot. I'm going to return this to 5 and run one more. Performance optimization is really hard like this. As you can see, now we're getting marginal gains. It's really hard to know whether we actually are getting performance increases or not. When we get to this stage, something like JMH, the Java Microbenchmark Harness, will give us far better results, but we'll probably have to run it on a dedicated machine to avoid the sort of problem I'm getting at the moment with screen recording. You can see the issue in this graph here. This is with screen recording not running, and as we sit here with actually recording the screen, you see the temperature climb, until in the end the CPU will throttle because it doesn't want to get too hot. Okay, so we don't want to drive ourselves mad chasing marginal gains, but we know that we're spending a lot of our time in could be made from the letters in. A good way of getting major performance increases is to see what we could pre-compute. Because we keep on going back to our dictionary and asking the words whether they could be made from the letters that we have left, if we could compute something for each one of those words that helped us, it could be useful to us time and time again. Now we could pre-compute letter frequency. So for every letter in our dictionary, we could say it's got 2 A's, 3 B's, and so on, and use that to deduce whether 2 words are compatible. That might be worthwhile, although it sounds complicated, but there's a simpler version which is just which letters are contained in the string, ignoring the number there are. And because we're working in English and we have 26 letters, we can actually store whether each letter was present in 26 bits. And 26 bits will fit in a single int, and we can test whether letters are there with bitwise operations, which would be really, really quick. So let's sketch this out in our tests. In our anagram tests, I'm going to add a test down the bottom, and I think we'll call this word signatures for now. So what do we want from these? Well, we want to say that if we have 2 of them, so let's say the empty string to signature is the same as the empty string to signature. Now, this doesn't exist yet, so let's create that. And we'll just put it here for now. And we said we were going to use an int. And we get that test to pass by just returning 0. And I'll run just this for now. Okay. Now, we want the signature of A to be the signature of A. And we want signature of AA to be the same. And B wants to have the same signature as B. And BA have the same signature as AB. And for luck, we'll say that BA has the same signature as ABA. So the signature basically represents the set of letters that are in the string. Let's go and make that happen. And I think we'll do this in a mutable way by making this our result. Make it a variable. And then we're going to go through this character by character. And we're going to set a bit in the result for each one. And we want the bit number of A to be 1. So let's spell that out. The bit number equals the character minus whatever A is. In fact, so the bit number of A will be 0, in which case. Now to get an int with that bit set, we take 1 and we shift it left by that number of bits. And then we take that and OR it into our result so that we've got whatever bits we already had and that one. So we say result equals result or an int. Let's just see if that passes the test. Well, it does. And we can also just see whether our representation is what we expect. So what we expect is that the empty string will have a signature of 0, A will have a signature of 1, AA will have a signature of 1, and B will have a signature of 2. So here we're testing the actual implementation rather than the behavior, but it's good to know that it's working as we expect. I think we can come in here and inline that and that and check it still works. Okay, good. Now what are we going to do with this? Well, let's take it out of here and move it into our anagrams as an internal function we can use. And now we want to pre-compute that for every word. So we'll give ourselves a data class. I think we'll call it word info. And we want to remember the word that it came from, which is a string, and it's going to need the signature, which is an int. And just while we make it compile, I'll make that 0 for now. Okay, so now we're going to go up here and say the thing we're going to process is not a list of strings, it's a list of word infos. And to make that work, here, we need to map each word to the word info given that word. And now each of our words here is actually a word info, so we're going to replace that with it.word. One more compile problem here, which is that this needs to be word.word. I think we'll make that word info so that we remember. Now that compiles, so it should probably pass the tests, and for now let's just run all of our anagram tests. Oh, it failed. That's interesting. Let's see why. And you can see here the issue is that we are collecting here this word info toString. So we're getting the toString on our data class. So what we really wanted in here was word info.word. And the same in here. Run that. And we're back to working. Now just to remind me what's going on, I'm going to make this into word info. And now I'm going to move whether a word could be made from the letters in something onto word info. So I'm going to take that away and say we'll create a method. Now we already know how to answer this in terms of just the letters. So this is return this.word dot could be made from the letters in input. And this needs to return Boolean. We'll run the tests again to check that is true. Good. So far we've just introduced complication and we've got this blank signature that's no good to anybody. Let's see how we want to use this signature. We'll go back to the tests. Now what we want to do is use those signatures to weed out words that can't possibly be before we check they've got the right number of letters. And I think that concept is has letters not in. So we could say that it's true that AB to signature has letters not in A to signature. But it's false that A has letters not in AB. Let's just use that to create an extension function on int. This is other and returns Boolean. Now each letter is represented by a bit. So we're actually asking the question, has the initial int got bits not set in the other? And the answer to that is return this ANDed with the other. And if that's not equal to this, then the initial int has bits not in the other, and so it has letters not in the other when we're treating the bits as letters. Let's just see whether that's true. Well, it passes, that's good. So now we'll make this into a nice little expression. And we'll just add some tests in here to check that it works in all the cases we expect. So the simpler ones, we expect it to be false that A has letters not in A, or that AA has letters not in A, or that A has letters not in AA. If those things are all true. And they are. Now we've tested that, we can make this internal and move it out of here into our anagrams. And now to use that, before we actually go through every letter in here, we can say if the word to signature has letters not in our input to signature, then we can't possibly succeed, so we'll return false. The opposite isn't the case. We may need two A's and only have one, so we still need to check here, but this is a pre-check that doesn't involve iterating through all the letters. We'll run the test to check it works. And let's just run a speed test to see whether it makes it faster or slower as it is. Well, that's 1.2 seconds compared to the 0.8 of a second or so we were running before. But the key thing is we're calculating everything every time here. If instead we calculate the signature as we build the word info, so this is word.signature, then we can use the signature directly in here. Let's try that. And that's now significantly faster. We're now 0.7 of a second. Let's see if we can get that down. At the moment we're calculating the signature for every one of these inputs, and we're using that up here. But this is constant inside this filter. So we should be able to use a word info here. That will let us change this to word info. This would allow us to use input.signature. And here we just have to use .word. Back up to the top. And we need to convert this into a word info on our initial input. And here we need to get the word back out again. And then wrap it again here. Let's run that. And that shaved another few tens of milliseconds, I think. And we do, of course, have to run our original test to make sure that we haven't broken anything. But that's good too. I think we'll just have a little tidy up before we check in. So let's go back up to the top and have a look. So we're starting with this mutable list of string that we're collecting into. We've now got this word info. I'm a little uneasy here about having the signature as a default parameter, because that would allow us to create word infos that had the wrong information inside them. So I think it would be better to have a constructor that took the word and called the primary constructor with the word and the word with the signature, and then make this a private constructor. As IntelliJ tells us here, that's still not completely safe, but it's a bit safer. Fix that. I don't know about the word signature. Signature implies a uniqueness that's not there, so I think maybe we'll call this letter set, letter bit set. How about that? And we could rename this to letter bit set. And now a lot of these things make a bit of sense. There's one more tiny optimization that might work, which is, although this is really quite cheap, the first thing we do here is this test. I think if we were to pull that out of here and move it into here, that would be this dot word dot length is greater than input dot word dot length in there. Then that would be a cheaper test earlier on. Try running our speed tests and just see that didn't make anything worse at least. I'm not convinced. I think that might actually be a little bit slower. Let's try commenting it out. Yes, it does seem to be quicker without, so let's get rid of that. Run again. We're back into the 600s, and I think we could probably reinstate that test there and run. Good. And note that I've left this in here, so I can get rid of that. If we put an else in here, then we can lift the return out of the if. And then this is not that and that. I think. Let's find out by running the tests. Good. Probably don't need that bracket. And now this is a single expression that might lay out better like that. One last little thing, and that's this if else here. I think that's a bit confusing. If we invert the sense of this, then we get if the remaining letter is empty, then we use the collector. Otherwise, if the depth is greater than 1, we reprocess. That then allows us to combine these. And then that we can make into a nice case. So when the remaining letter is empty, we use the collector. Otherwise, when the depth is greater than 1, we process. Run the test to check. Good. And then another one I've noticed here is we're using input word minus letters in word info word. It'd be a lot nicer if we were just able to say input minus letters in word info. If we did that, then we could add that in here, with other. And we know that this is that. Convert that to expression body and run once more. Oops, I messed up. I got a Stack Overflow because I forgot to put other dot word. That's this dot word minus letters in other dot word. And run. Phew. I'm now going to run the performance test with the screen recording turned off just to check that we haven't reversed our speed changes there. And there we have it, the low 600 milliseconds. Comparing to our baseline, which was 1400 or so, it looks like we've comfortably doubled the speed of this code, at least for this particular anagram. So I think that's a good point to check in with use word info. One warning. Oh, we knew about that. In fact, we don't need to make this a data class at all, really, because we don't compare them. So we'll run the test just one last time to check that is true. And commit. Phew. If we compare our code before and after these optimizations, we see that we gained this word info as a new class. But apart from that, actually the structure is much the same. And our optimizations are hidden inside this word info class, that we get the same sort of interface as we have for string. And then down here could be made for the letters in and minus letters in, both more complicated, but that's hidden down in the bowels and was just because they were running slowly. There's one last obvious thing that we haven't tried, which is running this code on multiple threads. There are two reasons I haven't tried it. One is this mutation of remaining candidate words here that we use to prevent us generating duplicate anagrams. If we partitioned our words up here and ran them on separate threads, it's not at all clear to me how they'd interact. In addition, I have half an ambition to run this in the browser with Kotlin.js, and I don't know the threading story there. I suspect that it would make things a lot more complicated. The code for this project is available on GitHub. Details are in the show notes. So if you can see an optimization that would help, please submit a PR. Or contact me and we can pair on it. I'm offering a prize with a signed copy of the Java to Kotlin book to the best optimization. But if you haven't already got a copy, you could click on the link in the show notes to read the reviews and see how to buy one. Thanks for watching.